cover the introduction to the talk yesterday by Carl, where he paradoxically apologized for not making a joke. So I thought I'd start by telling you what I'm not going to talk about, because I received some questions at dinner last night. I'll talk about sensing networks or secure networks or adaptive chaotic networks, so if you want to ask me about that, catch me at dinner this evening. What I do want to talk about is IP networks, and in particular wireless networks, and what the work on these networks has led me to think about networks and how they evolve and how people interact with networks. This is a summary of what I'm going to talk about. I'm going to basically spend most of the time making an observation that modern networks operate on principles which, in a sense, mimic the way people communicate. And that is because people built the systems. People are explicitly or implicitly building into the networks their own social behaviors. This leads us to a suggestion about how we can engineer new channels of communication. And then we can speculate, because this is perhaps one of the reasons for this conference, is to speculate about new possibilities. And we might speculate about what might happen to our brains in the future. So I'm not going to talk explicitly about evolution, but a lot of the issues, I think, will relate to how our brains might be evolving at this point in time. So that they don't hold responsibility for the speculations, I'll start off with the acknowledgements to the people who helped me work on the IP networks and the wireless network. ATR at Tokyo University of Electronic Communications, University of South Australia, and AC Communication Systems. So very simply, if we look at the modern communication network, we can think of it in 3 layers. Actually, there's a lot more layers, as you will see later on. The first approximation is to look at it in terms of 3 layers. The top one is the functional one. The reason we build the networks is because we want to use the networks to communicate. And the next layer below that is the logical structures which support the links between people. And at the very bottom layer is the actual cables and the wireless beams which carry the signals. So just to comment briefly on what's going on at the moment, I don't really need to cover that, but you're all very much aware of it. The fact that the use of networks is becoming a daily part of everybody's lives. People are using them more and more to share information, start off with sharing documents. Now people are twittering, they're sharing their current status on the timescale of minutes. This is really pushing the evolution of the network to support more and more of this real-time, large-capacity, interactive activity. At the bottom layer, of course, there's the physical stuff which is going on, which, of course, provides physical limits to the activity which goes on at the higher layers. And you're all aware that optical fiber is being deployed at great rate. Wireless networks are moving from 3G to 4G. You have local area networks, personal area networks, body area networks. There's more and more wireless exchange of data on smaller and smaller scales, which means that it's no longer just people to people, but people interacting with objects, exchanging data with objects, or exchanging data with other people via objects in their immediate vicinity. And then to connect these 2 layers, the demand and the actual physical circuit layer, there's a lot of stuff which is going on in between, and that's the main focus of the talk today. And obviously an important element is that it's based on packets and switching of packets. That's one of the great innovations of modern communications. There's multiple layers of control going on, which support the great variety of communication. And the complexity of the higher layers is supported by these organizing principles because they are sharing, all of these signals are sharing space and time and they're constrained by physics, just as everything else is. But you need some organizing principles to allow you to share space and time so that the people who want to interact can interact and the people who don't want to interact don't have to interact. And in this sense, those sort of principles are probably in common with great biological systems, certainly higher-order biological systems are organized. They have to exchange signals between remote processes, but they have to share space-time to do that. So they have to do a lot of organization, not just to use the information that they're exchanging, but actually to actually exchange the information. So you could go one step further and say actually the communications is the organizing principle in the organization, and what it does with the communications is just play. So in a comment, the organization of the networks is now involving more and more self-organizing principles, and the idea is to have communication processes on one layer, organizing socially, that is cooperatively, to support the end-to-end communication process on another layer. This is basically the theme of today's talk, and I'll give you some examples. I'm going to start with a popular area of research now, is VoIP and ad hoc wireless networks. Then I'll talk about some social issues which arise in these networks and the mechanisms which are used in the networks. So this is an example of an experimental system that we work on. This is done at ATR in the south of Kyoto. Here's a system of 50 nodes. There's red nodes are PCs and blue nodes are smartphones. And they all communicate using Wi-Fi. And they communicate in ad hoc mode. And for those of you who are familiar with it, most PCs support ad hoc mode if you want to communicate directly with another PC without having to rely on an access point. When you're doing a one-to-one communication with a PC, between a pair of PCs away from the rest of all the other wireless interactions, it's a fairly simple mode to operate. But once you have a number of nodes all together and sharing space and time, then the organization which is required to operate these ad hoc networks quickly becomes very complex. The other constraint is that the range of wireless communications is limited, so that nodes have to cooperate to communicate with remote nodes. People who they can't see directly go beyond their horizon. In this case, you have a node here. This is like a corridor of a building. There's another corridor down here, go around the corner, and the other corner of the building, this node wants to talk to this node. Specifically, the guy is going to use voice. It could be Skype, or it could be a special purpose VoIP software to communicate with somebody over in this corner of the building. But the radio signals don't go there directly, so they have to be relayed via other nodes. Now this is an ad hoc network. That means that all of the nodes are equal. Everybody's a peer. There's nobody who has any a priori special function. So there's no one to immediately tell everybody how to get the signal from A to B. There's another problem that they have to face, and that is that it's a physical environment. So it's complicated. It's fluctuating in time. And before a lot of this wireless work was done, before the wireless devices became available to make it easier for people to do these experiments, there was a whole generation of computer simulations by network people who were saying what wonderful things you could do if you had a wireless link. But most of the computer simulations didn't have real environments in the simulations. So they took a network simulator which worked for wired networks and put some protocols, several protocols, and then simulated what they expected a wireless network to do. But actually, a wireless network is a completely different beast because the radio signal fluctuates in time. So people would say, well, ad hoc networks are okay as long as you don't move, because you have to constantly reorganize if people move. The point is, you don't have to move. You have to constantly reorganize even if you're not moving, because the environment is moving. The environment is dynamic. So the fluctuations in the radio signal that you get in any natural environment cause a change in the quality of the data that you're receiving. And this is not a trivial process depending on how you're receiving the data, but in this example, for example, you have some packet loss. It's highly correlated with the drops in the radio signal, but it's not a one-to-one mapping. So you have some difficult decisions that the device has to make autonomously because nobody's going to tell it what to do. And that is whether it should use this link or not. So just going back, between every pair of devices, you will have some sort of fluctuation like this. So each pair of devices has a fluctuating link, and it has to decide whether to use that link for transmitting data or to use some other link. Now this is an example of good data in an experiment like this. And the bottom data shows the packet sequence number, because if you're doing voice over a link, you're sending packets at a fairly constant rate. And so the bottom here is the packet sequence number. And then the vertical axis shows the number of hops that the packet went over to get to its destination. So you can look at the packets which arrive and see how many hops it went, because it keeps a record of how it hopped. Now this is during the streaming of the signal. In this case, it's not actually voice, we stream music because it's tough to keep talking for a long experiment. So we usually stream music over. So this is music streaming, so there's a constant flow of signal. And the hops are constantly changing. The minimum is about 3 hops, as we saw in the earlier figure, to get from one end of the floor to the other. But in time, it has to switch to 4 hops, 5 hops, sometimes 6 hops, because the radio signals on the link are fluctuating, and the devices are spontaneously making decisions to send the signal over this way instead of this way. Nevertheless, if you look at the delay in the packets, it's also changing. It has a high correlation with the change number of hops. But each hop doesn't take a lot of time. So from the point of view of VoIP, voice over the radio network, this is a tolerable delay. So you wouldn't notice it if you were communicating. So the point is that the layer below is constantly reorganizing, and it's changing parts in space. And there's some change in the characteristics corresponding. But at the upper layer, you wouldn't know that this was happening. You just have a constant link with the person at the other end. So now I'm going to make a comment about some social issues. What do I mean by social? The theme of the talk is that we're not directly talking about people, we're talking about people have injected social behavior into their networks. So the way that these ad hoc networks operate reflects very much how people would imagine they would cooperate. If they were the 50 nodes in the room, they had to somehow arrange to send a signal. The trouble is, it's one thing to say, okay, let's cooperate and do it. The other thing is to agree on what you should be doing. And here's a good example about what is optimal, and optimality and fitness is popped up in other talks. The idea is that if you increase the send rate, so if you go up above the normal VoIP rate, what you might want to do if you're exchanging files, you want to download something, for example, from one node to another, you try and go as fast as you could. And then if you look at the receive rate, then when the send rate is small, you have a linear relationship. And this is the regime, this classical engineering regime, the way NTT used to build its networks. That is, you can build them with a lot of capacity so that they're not overloaded and so the performance is guaranteed. But if you increase the send rate, then eventually you're going to saturate because the links can't carry any more data. There's a maximum throughput. This is actually lower than the maximum bit rate because you have some overhead to controls. But the point that I want to make here is that before you reach the maximum throughput, you actually have an onset of instability. This is familiar with systems theory, that as you increase here, you have more and more stronger interactions between the nodes, and you go through a whole sequence of bifurcation points where things get more and more complicated, and you end up with packets behaving in very complicated ways. So initially, you're sending at a constant rate, and the receiver is receiving them at a constant rate. As point is that if you're trying to send a VoIP signal which requires, which you don't want a large jitter because it will affect your senses, then you want to stay down here. If you're doing a file download, for example, you want to push it to the limit because you don't really care about the jitter between the packets. You're only interested in how long it's going to take you to finish the download. So that the users, we have some organizing principles going on to support flow of data on the upper layer, but the users on the upper layer may have different expectations about where they want the system to operate. So somehow you have to build in some mechanisms to either make rules about this or to regulate this behavior dynamically, like introduce some negotiation. The next issue is what is fair. So we've built a society of peers, that all the nodes are equal in principle, but actually not everybody is equal. This is becoming more and more of a problem now, actually, than a few years ago, because now there's a huge difference in the performance of wireless devices. So you may have a wireless device which operates on 6 or 10 or 11 megabits per second, and someone might have a new .11n device which claims to run 100 megabits per second. So you have very different rates. And the problem is when people use the same devices in the same environment, because they're sharing space-time, you have this problem. The guy with the fancy new fast device is not getting any more throughput than the other guy. And that's because the social principle is one of equality of access. So that every time the link is free, in other words, there's no signal, then there's a statistical process which decides which node is going to transmit, but it's a symmetrical process. It doesn't depend on the potential rate that the device can operate at. So it means that if you have a node which sends a packet really quickly and finishes sending a packet, it has to send the next packet, it has to compete again with the other nodes. And if you have a node here which takes a long time to send a packet, then you have to wait. Then next, if you're lucky, you get to send again. But on average, you get to send the same number of packets, but the point is, this guy can send these packets much faster, but the throughput is not increasing. So now people are trying to figure out how to solve this problem, whether there should be a negotiation which allows people to say, well, I can go faster, so I should be able to send more than one packet. But this is not just an engineering issue, actually, it's a social issue, because this sort of thing happens in our society all the time. So what is the principle of equality that you want to implement in your system? And I should mention that this is an area where a lot of manufacturers of wireless device do all sorts of tricks to make sure they're sending more data. The next social issue that we have is the question of who is we? We have a peer-to-peer, I start off with a peer-to-peer network. It's okay if that's one network. Another problem that you run into with these wireless networks is if you have a network over here which has got up and running, and another network over here which has got up and running, because the self-organizing protocols are all nicely synchronized and coherently organized, then suddenly a guy in the middle switches on his PC. Up until now, this cluster and this cluster haven't been able to see each other's radio signals, so they've gone off in different directions, chosen different time arrangements and so forth. This guy switches on and can see both networks. And suddenly you're left with a dilemma as to whether this should be one network, or whether, because they have a different history, they should keep operating as two different networks. And this is basically what destroyed most of the first generation of ad hoc wireless experiments at many universities throughout the world, because this sort of mechanism was not built into the simulators which came out of the wired networks, but it was there in the protocol, so that depending on who you bought your chip from, the social behavior would change. The chips from some companies would operate on the principle that this should be one network, so that one cluster would have to synchronize with the other cluster. This led to very long transients as the clusters took time to reorganize. Now, how does, I've talked about the effects and principles, but I haven't really gone into how the mechanisms, and I'm just going to briefly talk about that now. And the key word to remember is peer-to-peer protocol. The point is a protocol, and way of thinking about these systems which parallels the rules of physics in other systems, where you have forces operating between systems which define their dynamics. In a network system like this, it's the protocol which is specified, which tells how devices interact. And this protocol is basically their natural law of interaction. And even you can imagine, even if the law of interaction is quite simple, it can lead to very complex dynamics. I'll give you a couple of examples. I just mentioned the components of a protocol. One is packet structure, and this is you typically have an address and who you want to send it to next, and there's some information about what the packet is and then the data. And you might think this is something like a gene, and a lot of the design ideas which go into these packets, I think, reflects those concepts. And the next is a node table, and I'll skip over that. The next point that I'd like to make is protocols don't operate on one node; they operate on multiple nodes. And the great idea which has gone into the internet, which I'm saying it reflects our own social behavior, is the idea that you build a protocol end to end. You don't worry too much about what goes on in between. And you have multiple protocols operating at different layers, and these are all operating autonomously. So the protocol defined at this layer just depends on what this guy sends to this with that protocol name. So that your packet have to reflect the fact that you have multiple protocols. So that from the point of this layer, all of this other stuff here is just junk. I don't know if it has something to do with genes. There's a lot of junk which goes on. This layer only needs to look at part of that packet to figure out how it should interact. And the interesting thing is that you have protocols when they go end to end. You may have like a voice protocol which has a software operating here and here, which defines the interaction of voice. But it has to run through a number of different protocols to actually get to the physical layer. And then it might go through some intermediate nodes, as we saw in the ad hoc wireless network. And here, they don't worry about the voice. They don't care about the voice. They've got all this voice data going through them, but they don't look at it. They're just worried about the protocol part, which requires them to relay it. So they look at whether the data is meant for them, and if it's not, they just relay it on. So a protocol diagram typically means that you have a line looking like this, which only accesses some parts of the protocol stack. And this great design means that you can have all sorts of different media on different hops. And this is what has led to the great flexibility of the internet. Now, this idea actually it just reflects something that we do in our social networks. If you think of trying to tell something, convey an idea to somebody by writing a letter, and how does that work? Well, you have the idea, but that doesn't get there directly. You have to express it in language, and then you have to write a letter and put it in an envelope, put it in a box, and then by some magic mechanism, the multi-hop gets delivered to the letterbox of the guy at the other end. And then he opens it up and then reads it, and then perhaps he gets the idea. So up until this letter part, this has been pretty well mimicked in the internet. And the point that I would like to make in today's talk is that higher layers haven't really been looked at very much. And that these higher layers are going to be important for integrating people more with their communications. So the internet was developed by injecting natural social mechanisms, and this mechanism allows systems to keep local freedom but still cooperate. So here we come to the speculation part. This is a good way to model and engineer brain-machine communications. And this is a borrowed picture by Bicentennial of a chip in the brain, which is communicating with an external device by radio. And I'm suggesting that on top of the lower layers of protocols, we can think about building higher protocols. So if you look at some of the things that have been done in the brain-machine interface at the moment, like moving a cursor just by thinking, because somebody's put some electrodes in the brain, then what happens is you have an idea and you send a signal which moves the hand, and the hand motion is detected, and then that's converted into a cursor motion, and then the guy that moved the hand might look that's where the protocol is, the sequence of the protocol is complete. He's decided to move and he's actually checked that it's moved. So there is, a lot of people focus on the forward flow, but actually there is a feedback loop which maintains this. And by writing as a protocol diagram, you can see that a lot of these processes are decoupled in time. It's not the tight synchronization that you would expect if it was a hardwired circuit. That's the great strength of the protocol. What happens in brain-machine interface? Well, you put in a new interface, which takes this signal and converts it into something else which can be conveyed along a different path, but still result in the same effect. And in some interfaces, it's the machine which learns the mapping between these two signals. And in other machines, in other setups, it's actually the brain which does the learning. So the brain looks at the signals which are sent and the effect, and this may be a very complicated nonlinear complex mapping. You think something and the person moved over here. If you do that long enough, you can learn a relationship between a thought and the motion of the person. In this case, it's the brain which is doing the learning. And the interesting part about this is that to do the learning, it actually has to generate activity here. If it was just a passive learner, it wouldn't learn anything. It has to generate activity and look at the responses to learn the relationship. So, that's a mechanistic suggestion. Now we start to get a little bit more speculative. The protocols I've talked about have been injected into the system by people, by designers. But the great thing about the brain is that it creates its own. We expect it must be able to create its own protocols. So at some layer of the hierarchy, there's actually a mechanism for the brain to create a protocol end-to-end. So the question is, if you have a new signal path, like a chip in the brain which is communicating the signal to a remote location, then the brain may be able to create a new protocol which is able to take advantage of the signal path, just by looking at the signal that you're going back and forth. This may relate to the generation of language, for example. Maybe it starts with pattern. But there's certainly trial and error, you can imagine, within the brain, which allows it to set up a new link, which was not there before because there's a new signal path. And so, brings us to the speculation. This is, I'd like to suggest, this is just off the cuff, but perhaps brains like new signal paths. I mean, I look at my children, they're not babbling, but they're teenagers, and they seem to be exploring all sorts of new channels of communication. And when they find a new channel, they set up new ways of using that communication. So, the technology for brain-machine interface is going to be providing lots of new channels in the near future. So it's not a question of do we need them. I think you'll find that once the channels are there, experimented on for medical or for education or entertainment reasons, the brain could take a liking to it. I mean, evolutionarily, maybe the brain is provided with a new channel, would like to use it. And can create the protocols to utilize these new channels. So once we start embedding chips, and it can be done technically, we can send signals. Now, the question is, I think we used to worry about, well, we have to understand the brain enough in order to do the coding to get to actually create an interaction. But I think our experiences are telling us now that the brain is very adaptive, so if there's a signal path, maybe the brain can find a way of using that signal path to make a communication over that channel. So that if we have wireless chips embedded in the brains, then we have all sorts of science fiction scenarios as to what the brain might want to do when it has those new channels. You'd be communicating before you're conscious of what you're doing. So I'd like to finish my talk by just summarizing that there's an observation that people are rejecting their social know-how in engineering of networks. So this evolutionary, this could be some sort of self-consistent mechanism and a way to organize complex organisms. You can suggest, as an engineer, you can imagine quite reasonably that we can extend, we can think about man-machine interfaces using the sorts of protocol concepts that we've used successfully in the internet, by extending them to include mental and social protocols. And that leads us to the final speculation that the brains may actually start to evolve in a completely new way once they're linked. So before we actually get to understand our brains, it may evolve away from